So I'm supposed to talk about the latest developments in CDG, and I think, in fact, you heard the very latest from the talks earlier today. I mean, what Ava talked about, that is the thing that to me is the most interesting and relevant to what you all experience and the questions you all have. So I think you actually heard the very latest because this was the article in yesterday's Union Tribune, which is a local paper, about the Omler family, and that Damien is the only patient in the world, and we scoured the universe to try to find the second patient that would have his deficiency. We couldn't find it. We looked for a long time. And so to be able to come up with this kind of a diagnosis, to find a new type of CDG, you say, well, what's really involved in doing that? How do you begin to go about that? And that's what I'm going to try to describe here a little bit and give you a flavor of where things have come from and how we get there, because I think we're not going to go into great scientific detail, but I think it's important to understand something about the journey. And so if we look at there, that is a graph that we have put together and built on over the years, and what it does is to show the growth of number of CDGs that we've had over the years, and we take this up to 2019, but in fact we know just from what we've heard here at the meeting and from what we know in our own lab, there are probably at least 3 or 4 more disorders coming, and whether it's actually 140 or 150 disorders, it depends who's counting and exactly where you draw the line saying this is a glycosylation deficiency or it isn't, but there's a whole bunch, and they've grown up really rapidly, and I think you can see that the most rapid growth is in the last decade. And so, not surprisingly, a lot of physicians wouldn't even be aware that these things are problems and would not know to be able to go to look for them. First one was a thing called eye cell disease that I worked on back in 1981. That was the first real CDG. So I'm going to talk about a new, I'm going to talk about how we got to the diagnosis of a very important deficiency. Now, if you put the word FUT8, that's the name of a gene. If you look for what has been done on FUT8 into the grand search engine of the National Center for Bioinformatic Technology, you come up with 197 references. And that started in 1997. So actually it was known before then, but then it was known as an enzyme and not a gene. That's sort of a bit technical, but this has been around for a very long time. And you say, well, how about telling me then how much for FUT8 CDG? Because there is such a thing. And there you have 3 articles. And the first article was one that we published with biallelic mutations in FUT8. And Bella, 2 years ago, we had just published the paper that included Bella as one of the first 2 patients. And I can tell you, her smiley face is on a little refrigerator magnet right above my desk. And so she stays close to us. Well, there were now just a paper accepted and just came out, which is called Expanding the Molecular Spectrum of FUT8 CDG. So why did it take so long to find the first case? And then kind of quickly we found the second cases. Well, what happens is that once physicians know to look for a particular kind of disorder, they're going to start looking for it. But they're going to run into certain problems. And part of the problem is if you find what's called a variant of unknown significance. That means a change in the amino acids, a change in the gene sequence. That is a change, but you don't know if it really makes a difference. So you have to be able to have some way to say that there is a mistake And that mistake causes the problems that you're seeing in the child. So the first one, we had to figure out how to approach that. We did. Then by the second time it came along, now because we had published this, suddenly we became a magnet where other physicians, other scientists would write to us and say, hey, I think we've got a patient. But what you have to have then is a way to know that those potential mutations are really damaging. And that can sometimes take a fair amount of time. And there was one paper that came out. I think this is interesting. It says that we report the first case of glaucoma in an infant with foot 8 CGD. CDG is not so well known, and you can misspell it, and hopefully people still know what you're talking about. But anyway, that's part of the glycosylation issues, but that's not true here. And we have, because we're able to do this, now we have a summary of all the 7 cases. And Bobby put together this very nice bar graph showing the kinds of symptoms that will come up in foot 8 patients. And I know someone asked us yesterday, well, is there, how do we know to recognize this kind of patient? Well, many different kinds. PMM2 has got a lot of diversity, but we know the kinds of symptoms to look for. In a lot of these disorders where there's 1 or 2 cases, you may not actually know that it can be much broader spectrum than that. So as you get more patients, as you find out more information about more patients that doctors are providing, you can then begin to stitch together a clinical profile. And every time you do this another time and another time and another time, you get more information and you get to see what's very consistent. We've done this sort of thing for, I think now, maybe half a dozen different disorders. So we have some confidence of what these patients are going to look like. Where there's only a couple, we may not know. We may be seeing the outliers. On the other hand, they may be dead center of what you can always expect. And we just don't know. We just don't know. That's why this is so important to get that out there. So now I'm going to talk about a disorder that we became involved with a number of years ago. And it runs into the same kind of issues that I was just talking about for foot 8. So this is an enzyme called CAD. All you got to know about this is it's a huge gene. It is over 2,200 amino acids. And that means it's big. Many genes are, on the order of 200 or 300 amino acids. This is large. Why does it have to be so large? Well, it's in part because the reactions, and those reactions are shown. Do I have a little pointer? Uh-oh. All right. Is that moving? No. I'll make signs. So every place you see on this little bar up at the top that's a different color, that's a different enzymatic reaction. But nature's found a way to put all of these enzymatic reactions together in one protein. So what happens is that you start out with sort of raw elements, and in the end, you make this molecule that is called a pyrimidine, and that's one of the components of an intermediate for glycosylation. So you may hear UDP, UMP, CMP. Those are molecules that act as carriers for delivering the activated material into glycosylation. So what's interesting about this is many of the mutations in this disorder delete the ability to make a molecule called uridine. But the good news is you can add uridine, and we did this in cell models and all sorts of basic science stuff. You can add uridine, and if you do add the uridine, you can get really great recovery. So what does that mean? Well, we did the first one on the lower left. That was the first patient that was described. And we said, you know, I'll bet you could give uridine to that patient and it would help that patient's seizures and developmental delay. And these were really quite serious. But we couldn't do it for bureaucratic reasons and licensing issues. So even though we could suggest it, we couldn't do the experiment. If you look on the right, somebody else then rather shortly after that came along and said, aha, we have some patients, we have a couple patients who are not doing well at all, but we know they have mutations in this gene. We're going to give them uridine and see how it works. And it was a miracle. It was an absolute miracle. Within a few days, they were starting to respond. And now you can see that over several months, the improvement was really phenomenal. The seizures had essentially disappeared, and they were going from almost like a vegetative state to going to major restaurants and ordering off the top of the menu. No, I'm kidding about that, but they they're phenomenal improvement. So now this was done that I'm going to talk about in collaboration with a lab in Spain, and this is from Paco Ochoa and Santiago Ramon. They came to us and they said, well, we have a way of being able to tell if one of these variants is actually a problem. And here's the issue. There are 2,250 amino acids in CAD, and there are 1,000 variants. You think about that. 1,000 variants. Well, every doc who says, I found 2 variants in CAD, and my patients have some of these generalized symptoms, I'll bet that they could be treated with uridine, and I'll bet they'd get better. Well, yeah, maybe if you actually know that those are mutations and not just variants that don't mean anything. So what they were able to do, and working with us, they were able to come up with an assay. What that assay would do is to take mammalian cells, didn't matter which kind, and completely knock out that gene. CAD gene was gone. So their growth was totally dependent on adding uridine into the cell medium, and that's shown on the figure on the left. So without uridine, there's no growth. With uridine, boy, do they take off. That's just fine. So then they used several varieties of different inactivated types of CAD mutations in the different domains, the different activities, and showed that with them, again, you didn't have growth. But if you provided uridine, you could get those to grow. So this was a nice assay. So what we're able to do with that then is to take all of the mutations, all of the variants that we were able to collect by having a number of different people come to us over the years with prospective cases. And down at the bottom, again, those bars, if you can see them, there are some numbers in red, there are others in black. The ones in red are the mutations that we were able to prove with this assay. And as you scan across the top and you look at each of those panels, A through D, what you see is that there are many of them that cannot be rescued by putting in the mutated version of that protein. And that means it was a pathogenic mutation. So if they get rescued very easily by putting in that prospective mutant, it means that, in fact, it wasn't a mutation. It was just a variant. It was one of those 1,000 variants that didn't really matter much. And so over the years, we had collected 25 different patients. Again, all having variants in CAD. And we were asked to figure out how many of those will actually be patients. And it was a bit of a shock. I will not go through all of this. That is a chart showing prediction programs. Now, you all may know about people can make predictions based on protein structure, based on history, based on evolution, about whether some variant is going to be damaging. There are 3 different prominent prediction programs out there, and what we found is that they didn't agree. So our assay, we know, is a good way to be able to do this. Those prediction programs didn't agree. And in fact, what we found out was that only about, I think it was 40% of the variants agreed in all three prediction programs and in our assay, our functional assay. So that means you've got to be very careful if you're a physician in talking about what you will be able to do for this patient, and does this patient actually have this disorder. So you need to have this functional assay, and that's what we've been able to develop here. And we put together a bobbygram, as I call it, and that shows you now all of the 10 cases that we had, because out of the 25 suspected cases, only 11 of them were actually cases, and therefore you would think would benefit from uridine. So you can see that it's very typical up at the top that all of the patients have intellectual disability, developmental delay, seizures, and about half of them will have feeding problems. But one of the things that was thought to be always typical of these, and now we see that it may not be true, is that they have an anemia. All the patients that have been found before had funny shaped red blood cells and anemia. But we find in this new group that only about 40% of them have. So if a doctor is relying on those general symptoms plus the anemia, you might miss it. So how many then of all of these cases that we've been in contact with the physicians, you're probably saying, how many of those are now on uridine? And you would think, all of them. No, one that we know of. And here's part of the danger, and it goes back to what Ava was talking about, and that's that you can go to Amazon and you can buy uridine of unknown purity. You can buy super uridine of unknown purity. But if you go off and do that, we lose the ability to actually know what a proper dose is, how it should be done, what the reactions are if you're doing it on your own. So we encourage anybody who may go on uridine. We hope some of these folks are in the Middle East and far away from places where they can get uridine, but we would hope they would get it in time, because it can be an absolute life changer. And many of these patients have died without uridine. So it's a lifesaver, and I think this goes back to something I said before, which is this is about the ecosystem. We all have to be together in this. Symbiosis works. Basic scientists have to collaborate with physicians. We are no place without you. And we may, your physicians are interacting with the families, that's clear, but coming to us as basic scientists and us being able to give back in terms of what we know about the importance of these assays is something we think is going to really make a difference. So we always start with the patients, and then we move toward basic science. And again, it's a cooperative back and forth. So join the ecosystem, stay in the ecosystem. We're all together in this together. All right. Thank you.